By looking at these two graphs, you are able to derive the formula for focal length. The standard formula for any graph is y equals mx plus b. So, by substituting the variables, we can derive the formula. Since the inverse of DO is on the y-axis, we substitute it for the y value. On the x-axis, we have the inverse of DI, which we then substitute in the equation. Once you have plugged the variables into the equation should read, the inverse of y is equal to the negative inverse of x plus b. Next, rearrange this equation so that the intercept, which is also the focal length, is equal to the inverse of x plus the inverse of y. Now the equation should be read as b is equal to the inverse plus the inverse of y. All you have to do now is substitute the variables in the graph for the equation. X is equal to DO and y is equal to DI, which leaves b to equal to f. The equation should now state the inverse of f is equal to the inverse of DO plus the inverse of DI. So the final equation is 1 over f equals 1 over DO plus 1 over DI. We basically got this out by finding the relationships from the graph.
In this lab, we learned about the focal lengths located in mirrors. We could have had many sources of error, such as measuring the distances incorrectly and incorrectly finding the focus based on the image we see with our eyes. To avoid incorrect measuring, we can use an easier method that we prefer, such as a meter stick. In order to eliminate an unfocused focus, all of the group members should check the image to confirm that it's focused correctly. A use of knowing the focal length is used in passenger side mirrors in cars, which is very important for the safety of the driver. Overall, this lab helped us derive the equation for the focal length in 2 different ways, which we can use to apply in the real world.